So I'm Rod Sheeter. I'm the tech lead and manager of Google Fonts.
Hey, and I'm Garrett. I'm the tech lead of production for Google Fonts.
And I wanted to call out that there were on the order of 10 people, both within and without Google, who kind of contributed related work. So we're not claiming that we did everything. We're just kind of here to talk a little bit about what the end result was. So I thought we'd actually start at kind of a higher level and talk a bit about what's Google Fonts. I imagine this audience kind of has some idea of that. And perhaps also why Google Fonts and why do we care about serving Korean in the first place. So at a very high level, Google Fonts is a free open source collection of fonts. We provide fonts to a bunch of Google's products. You can go in Google Docs and stuff and use all our fonts, various other Google services, and also for free to the web at large. So we provide the fonts open source and we also provide free serving. And occasionally people have asked, why would you do that? Like you're basically burning money. We literally have a bunch of Google servers sitting there serving fonts to billions of web pages just for fun. And the underlying reason is that kind of maybe slightly less as more and more hardware comes out, but Google plays on the web. Google operates on the web. Anything that's good for the web is good for Google. And this is ultimately the rationale to run Google Fonts and offer the serving for free. So one of our goals is, of course, to serve all of Google's users. And it turns out we have some that would like to use CJK, so not having any Chinese, Japanese, or Korean has been a long-standing gap for us.
Okay, yeah, so I'm really happy to announce that we have Korean fonts live on Google Fonts now. We have 23 families at present. If you're interested in finding these, it's really easy. Just go to our homepage on fonts.google.com and change the language drop down here to Korean, and you will get all of our Korean families.
So we've been operating for a while, so you might wonder, what took you so long? Why didn't you serve CJK much sooner? Because people have definitely been asking for it. There's a couple of reasons, and they kind of compound one another. The first is that it costs quite a lot to transfer the definition of a CJK character. It's just more complicated. This is kind of then in turn compounded by the fact that there's just a lot of them. So it turns out there's an awful lot of the web that you can render with a couple of hundred Latin characters. There's a big chunk more that you can render if you add, I don't know, 1,000 more characters. By contrast, in order to do Korean, we need an enormous amount more than that. And then for us in particular, we don't want to ask people to trust JavaScript from Google Fonts. This is kind of something we're trying very hard to avoid. So we want a solution that works purely with CSS. And to give, I guess, specific context, we can create a minimal set of Korean that will service some pages, and it runs to sort of 5,000 glyphs, and they're, of course, the more expensive glyphs. But to get something that doesn't constantly have problems with, there's a couple of characters where it breaks out of the font, we need well north of 10,000, which is kind of a problem to serve. And I wanted to kind of illustrate this a little bit. So Nanum Gothic is a family that was kindly open sourced. If I take the whole of Nanum Gothic, try and serve it as a WAF 2, it's 1.7 megs. This is kind of ridiculous to deliver to people to render text, in our opinion. We're trying to make the web better and faster, and this is kind of actively making it slower. If we cut it down to the subset of, I think it's a little over 5,000 characters, which we kind of deem to be Korean minimal, which doesn't really work for all the pages. They tend to have this problem of being missing a couple of characters. It's still coming in at 600K, so this is really not working at this point. And just by way of contrast, Roboto cut down for a device like a mobile phone that doesn't require hints in WAF 2 with just a couple hundred glyphs can come out in sort of 15K, and that's a lot better for us. And even a slightly more complete copy of Roboto is still just 200K. And to kind of illustrate the source of the problem, the character on the left, relatively simple, brings a couple of hundred of its friends. The character on the right, relatively complex, and is liable to bring north of 10,000 of its friends. So transferring this is just vastly more expensive.
All right, so today to speed up font transfers, we use subsetting. So for most of our fonts, we can split them into subsets based on a few scripts. When the user goes to use that font, they can choose which of those subsets they'd actually like, and then we just give them that one subset, and generally that works pretty good. Unfortunately, that's probably not going to work for us for CJK. First of all, there's not really a good way to split it up into subsets. You kind of just need the whole thing, and so the whole thing you need is just too large. All right, so then we wanted to set out some requirements for what our Google Font Serving solution should satisfy. So the first big thing is we need it to support cross-site caching. This is one of the key benefits of a centrally hosted font service. And what this actually means is that you can have one copy of a font cached and then reused across many websites. So, in that way, the more times a font's used across the web, the faster it's going to be for everybody. And Rod touched on this earlier. We wanted our solution to be CSS only, and even more concretely, it should have no API changes from how it works today. So our current API aims for simplicity and ease of use. We didn't want to complicate that by having a second way of using things. So in that way, it should just work like any other of our Google fonts. And I guess I should point out one of the big benefits of our CSS API is it allows us to deploy ongoing optimizations. So for example, when Wofe 2 became available in browsers, we were able to roll out support for all of our users, just in the matter of a few days. And likewise with Korean, as we improve and make it faster, we should be able to roll out those changes to all of our users.
All right, so we wanted to touch a little bit on some of the kind of foundational work that our solution builds upon. And first up is Wofe 2. Shout out to Vlad, who's hopefully out there somewhere, for kind of making it happen and herding everyone along. Wofe 2 just straight up takes a font file and makes it smaller, which is great. So it rewrites some of the way that glyphs are expressed, and then it compresses everything with a brand new compression scheme that some compression folk in Zurich were kind enough to come up with for us. And the net result is that as compared to the best zip we can achieve, so kind of spending as much CPU as we can to come up with the absolute best zip we can create, it's still 25 to 30% smaller. So this is a huge win for us, and when we deployed this kind of for our users, their websites got a little bit faster. To illustrate the effects, if we start with Nanum Gothic again, it starts off over 4 megs. If we zip it, it's 2.3 megs, and as Wofe 2, it's 1.7. And at this point, you're getting back the same font. We haven't trashed the outlines or kind of done any damage to it. Second optimization that we've gotten a ton of mileage out of is Unicode Range. So Unicode Range allows us to say, I'm going to cut this font in pieces and tell the browser about them in advance. So here we're telling the browser, this pointing thing is kind of weird. I have one piece which has Cyrillic, and here's the range of code points that make up Cyrillic. And I have another piece that is Latin, and here's the code points that make up Latin. So if you go to a website that uses nothing but Cyrillic, it will download only the first piece. If you go to a website that uses only Latin, it'll download the second piece. If you need both, it'll download both. You also get really nice caching benefits where if you go first to a site that uses Cyrillic and then a site that uses Latin and Cyrillic, first you'll download Cyrillic, and then on the second site, you're like, oh, well, I also need Latin, so I'll go and fetch that. And a good example of where this has been a huge win for us is things like maps, where they can display a fairly wide range of characters, and it's a bit hard to predict in advance what they'll need. But a lot of people just look at maps of, say, America, and they don't need a whole bunch of characters. So for them in particular, and for various other Google properties, this was just a massive win. And as is kind of intended to be illustrated in the URLs, Wofe 2 is just works great with this. It makes all the pieces smaller. So this is an attempt to illustrate the combined effects of these. It's from a blog post we put up actually in 2015, but it still holds. So HTTP Archive tries to track what's going on the web, and the blue line shows that basically people were using more heavier fonts over time. So the number of bytes that are being pulled for pages is just kind of going up and to the right. And unless network speeds are keeping up, which seems unlikely, the web's just getting slower here. So then the red line attempts to estimate the impact of rolling out Wofe 2 on this. So we can see Wofe 2 comes out, and we estimate that there's kind of a big chunk taken out. A little bit later, we roll out Unicode Range, which is complementary, and now we've really taken a massive bite out of that. Still going up and to the right, because if you use more font, you still ultimately have to transfer more data, but we can kind of afford a lot more bytes now.
Okay, so let's figure out how we're actually going to ship Korean. So using Unicode Range and Wofe 2, we're going to cut our fonts into a lot of pieces. We're going to tell our browsers about these via Unicode Range and have it get the pieces it needs. So this sounds very simple. Unfortunately, though, the hard part is figuring out how to cut the font into pieces. The fonts have, say, 17,000 code points, and the number of ways you can group those is extremely large. So to start out with, we decided to kind of propose a few different ways we might try to segment these fonts. So I'll just quickly run through those right now. So the first one is equal bins. So in that, we just take the code points in the whole range, we split it into just 100 groups of equal size, and that's it. So we can get a bit smarter about this and do something like a frequency-based thing. So we sort all of our code points by frequency. We have 2 large groups of approximately 1,000 code points at the top, and then group everything else into 100 groups of equal size. So frequency compacted is a slight variation on this. It uses those first same 2 groups, but for the remaining ones, instead of sorting them by frequency, we just sort by code point, so that way you get really nice compact Unicode ranges and a smaller overall CSS size. And then finally, being Google, we like machine learning. We figured we'd throw some of this at this problem. So we set up a topic model that treated characters as words. We tried to find out which ones kind of co-occurred with each other, and then threw a genetic algorithm on top of that to balance having a compact CSS against a smaller amount of font transfer, and then that spit out a strategy at the end for segmenting the fonts. Okay, so we've got all of these segmentation strategies. We've got to figure out how to actually compare them to figure out which is better. So we set out a couple of criteria here which we would use to evaluate these. So the first is that we'd like to transfer the fewest bytes possible per page view. Also, we'd like to minimize the number of actual font requests made per page. Unfortunately, you can't have both of these at the same time. They're often in direct odds with each other. So I'll just give a quick example to illustrate this. So here we have a graph, and as we increase the number of segments that a font is cut into, we would expect that the delay for transferring bytes is going to come down. This is because as you have smaller segments, you can get more accurately the code points that you actually need, and then you don't need to download a bunch that you don't actually use on the page. However, as we increase the number of segments, we'd expect that there's going to be additional delay on the network stack due to having a large number of requests that need to be made. If you need to make 100 requests on a page, it's going to jam up your browser's request queue and just take a while. So if we put these together, we're going to get a total loading time in it. So it looks like there's probably some sweet spot somewhere in the middle of this space, and that's what we want to try and aim to hit.
All right, so to start off, just to kind of sanity check how things look in the real world, we went and took a look at a bunch of actual pages using Korean. And I'll just talk about 2 of those examples. So one of them was a Korean YouTube video of, I think, Olympic figure skating, plus a bunch of comments. And when we look at that page, it uses sort of 1,800 characters, but only 394 of them are unique. So there's a lot of reuse of characters happening on this page. Even more promising, if we go to a news site that has a super text-rich and rather long homepage, it uses tens of thousands of characters, but only 729 unique ones. Even better, if we look at the unique characters across both pages, there's only 734 that are unique. So what we appear to be seeing is that there are some characters that get reused a lot. And that's really good because that suggests that some of our strategies will actually work. So from this, we observe that, well, it's great that we can observe this one by one, but really what we need to do is go off and check this type of thing for a large set of Korean web pages. And just to kind of illustrate how strong this effect is, this is just on the 2 sample pages that I talked about. And you can see kind of going from on the left, the most frequent characters, and just showing the frequency to the right where there's the least frequent characters. There's a couple that are used well north of 500 times, and kind of a long tail showing up here. And this is, on these 2 pages, we only use 700 characters, whereas our set that defines Korean that we think will fit most web pages is kind of pushing over 17,000.
Okay, so we made some observations on samples. We wanted to actually go ahead and collect some real data on this and figure out exactly what everything's going to look like. So to get started, we defined a Korean set of characters, which ended up being about 17,000 total. Next, Google regularly indexes the web. We have access to this data. So we set out to pull out a bunch of Korean samples from that index and then look at them in more detail. All right, so for each of those sample Korean pages, we found the set of Korean characters that occurred on those pages. So for this analysis, we didn't actually care about the number of times a character was used on a particular page, just that it was present at least once. And then finally, we combined all that to count up the number of pages that were using each character. We just have a small example of what kind of the output of that analysis looked on the right here. All right, so this is the graph based on the data we looked at the index, very similar to the sample one that Rod showed earlier, but we see most notably there's an extremely largely used set, a small set of very frequently used characters. So this bodes well. This means we can probably find a really good way to segment these fonts.
All right, so then we had to actually go and do some testing to figure out which of our strategies actually worked. We spent probably more time than we should have kind of running simulations and trying different cost functions and essentially trying to figure out offline what the best solution was going to be, and basically learned that actually live testing is much better. So what we wound up doing to kind of get results we could stand behind was we took the strategies that looked promising and we sent each one a small percentage of production traffic. Let that run for a while, kind of long enough for caching effects to settle and all this type of thing, and then measured to see if any of them did any good.
Okay, so time for the exciting part, the results of our analysis. So first we're going to look at the criteria of the number of requests made. So this graph shows for each of the 4 strategies I talked about earlier, how many requests made relative to our all strategy. So we used, as a control, just a single large font file that contained everything. So kind of the important thing to notice here is that just about everything did fairly well. They only barely made more requests than all, except for the equal bin strategy, which kind of as expected causes an insane number of requests to be made for each page. So on the grounds of this, we've ruled out equal bins as a viable strategy. Okay, next. So now we're looking at the number of bytes saved using each strategy versus the control, which is just using a single big file. We're really blown away with how well we performed here. All of our strategies caused significant reductions in byte transferred. The best one was actually the frequency compacted strategy, which reduced bytes by an amazing 88%. So based on the results in the previous slide and this one, we selected frequency compacted as the winner, and that's the one that we've actually shipped with. All right, so we learned a few lessons on this. So first of all, sometimes simpler is better. You'll notice that the machine learning one, which we spent a lot of time on, didn't actually do that good. Turned out that just using a simple frequency-based analysis actually outperformed it pretty on both metrics. Next, there's kind of a common strategy that seemed to work very well, and that was using a few big segments at the start with a few thousand characters, and then a bunch of smaller ones to fill in the gaps and missing pieces.
All right, yeah, so we've got this kind of working for Korean, but obviously we set out originally to cover the entirety of CJK. So kind of what's coming next for us is we think we can save more bytes. So even though we're kind of only transferring 12% of the bytes that our control strategy originally transferred, that's still more than most pages actually need at an absolute minimum. So we think there's kind of room to squeeze more out and make things faster, which is great because as Garret mentioned earlier, we'll be able to transparently roll that out and people who are using our Korean will just get faster. We also, despite having spent probably inordinately much time on it already, kind of want to beat our naive solution still. So we'll probably take another crack at the machine learning thing and see if maybe the problem is that we had a bad cost function or somehow we've got something wrong going on in there in hopes that it can come out with something that actually outperforms kind of frequency analysis. And of course, we want to investigate Chinese and Japanese because we have users there as well. one piece of very good news is that we have done a preliminary analysis of the frequency of usage of characters in all 4 here. CJK somehow needs to expand to 2 Cs. I haven't quite figured out how to do that. But for simplified Chinese, traditional Chinese, Korean, and Japanese, we're seeing for all of them that there's a really strong high usage block of quite a lot of characters, but relatively few, and then just a long tail that's used occasionally. So if we can find a model where most pages download a couple of segments of very frequently used characters, and maybe like 1 or 2 of the rarely used ones, they're still not downloading 90% of the font. So that's great. And then we haven't entirely confirmed this through a real analysis, but there's a rumor that Japanese tends to use more open type features, and open type features snap if you put them in separate Unicode ranges. So that might mean that we cannot freely subset. We have to kind of be careful about that, either avoid snapping any or decide that kind of really rarely used ones are okay to snap. We're not sure yet. So that's all we have for today. There's a couple of pages that we thought we might direct people to. So first is fonts.google.com, subset Korean. We'll show you our Korean collection. And then on Google Fonts, GitHub.io/Korean, Dave has worked with a bunch of people to put together a really cool demo of some Korean stuff. And with that, does anyone have questions? Fire away. Thank you.